All right, it's about time to start. Good morning, everyone, for those in the U.S., and good afternoon to those in the U.K. Today we will have two presentations. The first one will be about the Scientific Web Information Management System, also known as SWIMS, and the second one will be about the metabolomics data analysis for heart failure patients. Today's presentations are scheduled to end around 10 a.m. Pacific time, so each presentation is about 30 minutes. Again, these conferences are recorded and accessible online after we process them. If you have any questions during the presentation, please type it in the message box provided in the application. And also please mute your mic during the presentation to prevent any background noises. Are there any questions before we begin?
Okay. So, hello everyone. My name is Shigao. I'm a PhD student from Web Information Systems Lab at UCLA. Today I represent our Scientific Web Information Management Systems. We call it SWIMS with Dr. Massimo. So let's start. So as we know, the internet has brought us a great deal of information. We have many knowledge sources in the web. We have Wikipedia, Yelp, IMDb. Among all these knowledge sources, Wikipedia may be the most famous one. It's a semi-curated web content corpus used by billions of people around the world. And also, it supports more than 280 languages. Its English version has more than 4 million articles. So basically, we can get everything we want from Wikipedia. The text, info box, image, and videos. At the same time, we also have some structured knowledge base like Freebase and DBpedia. We take DBpedia as an example. So DBpedia, it organizes the information taken from Wikipedia info box and store them as RDF triples so that we can support SparkQL and other structured queries on DBpedia. With this big knowledge base, we can support many interesting web applications. First, we can greatly improve the quality of web search because structured queries combined with text-based queries will return higher quality results with much better precision. It can identify the query results with the help of the values of entity properties. And also, many other semantic web applications such as natural language queries, data integration, knowledge-based integration become feasible. So the knowledge base are very powerful and helpful, but there are some problems that restrict its effectiveness in scientific applications. The first problem is usability. Because SparkQL is only available for experts who are familiar with the syntax of SparkQL and the internal terminology of DBpedia, which means that normal users are excluded. For this, we developed two solutions. First is web system. It's developed by Professor Carlo and Professor Mazzeo in Italy. In web system, it supports user-friendly structured queries, which means that user can just find an example page, click on the attributes they are interested in, and fill in the query conditions. Then our system will generate an equivalent SparkQL query and run it in backend SparkQL engine. The second solution is natural language queries, which is proposed by Dr. Massimo and Professor Carlo. Because sometimes users are more comfortable with natural language questions, so we try to pass the natural language questions and then generate equivalent SparkQL query and also the swipe page. The second issue is incompleteness in this knowledge base, because these knowledge bases are mostly constructed by human efforts. So it's not surprising to see that there are many pages without info box. And also, many existing info boxes are incomplete or inaccurate. So we propose IBMiner system to extract info box from free text to complete and verify existing structured information in the knowledge base. The last issue in current knowledge base is provenance and temporal queries. As we know, the knowledge in real world is always changing. For example, the number of students at UCLA is changing. The mayor of area is changing. So these changes will be reflected to the knowledge base. And sometimes users may want to ask questions like, what's the number of students at UCLA in 2009? Or who served as the mayor of LA in the past 10 years? To answer and support this kind of temporal queries for knowledge base, we need a temporal extension of structured query language and an efficient implementation to evaluate temporal queries on large-scale knowledge base. So we propose a system called the SparkQLT. Here we prepare a simple example to show the problems in current knowledge base. For example, if we search the information of actress Rachel McAdams, we will first find her wiki page, and on the top right corner of wiki page, we can find the info box part. So basically, we can find her birth name, birth date, birthplace, occupation, active years, all this information. And also, if we do such search using SparkQL in DBpedia, we'll get a set of RDF triples as this one. And also, we will have free text. In these results, we'll find that first, there are some incorrect information. For example, in the DBpedia, there are 2 values for birth date. And it's very easy to find that the first value is actually incorrect. And also, some information in the wiki text, for example, the movies and the award information is not covered by existing knowledge base. So we propose the scientific web information management system. The goal of our system is to construct a general knowledge base with higher quality and coverage. To achieve this goal, we perform following tasks. First, we integrate and complete existing knowledge base so that our integrated knowledge base can cover many different domains. Then, we try to support query by example search over our knowledge base, so this huge knowledge base can be searched and explored by normal users who are not familiar with existing structured queries or the internal terminology. And also, we try to answer natural language queries, which is another actually more convenient way to search the knowledge base. At last, we propose our temporal system which can search and explore historical knowledge base. Actually, we propose a temporal extension of SparkQL and develop an in-memory search engine. So next, I will try to elaborate these tasks one by one. For the first step, we integrate existing knowledge base. We collect many different knowledge bases. Some of them are domain-specific ones, for example, musical fluency and field names. And also, we pass some general knowledge bases like Wikidata and DBpedia. By collecting this public knowledge base, we unify their representation to RDF format and integrate them into a central knowledge base. We call it IKB store. During this integration, because different knowledge bases, they may have different terminologies. For the same entity, they may have different names. So we use string matching, semantic similarity, and also some synonyms to align the category, subject, and attribute. The final result of our integration is a knowledge base with about 9 million subjects and 105 million triples. However, although this knowledge base is already very large, but there are still many information in the text not covered by this knowledge base. So we propose our text mining system called IBMiner, which can generate structured summaries from free text. The general workflow of IBMiner is as follows. We first develop an NLP tool called SEMscape to convert text to graph structure. Then define a set of graph patterns and perform pattern matching in text graphs to extract semantic links. Because the format of semantic link is very similar to infobox, but the terminology used by semantic links is not standard ones. So we learn patterns from existing examples to convert this extracted information into correct format. After learning these patterns, we got a mapping which can map the words in the sentence to correct attribute names. Then we will apply this mapping to our semantic links generated in step B, and then generates the final triples. So we prepare an example as this one. We start from Wikipedia, for example, the Wikipedia of Barack Obama, and we first apply our text, our NLP tool called SEMscape to generate text graph. Every node in text graph is actually a semantic part of this sentence. And the edge in this text graph is actually representing the relationship between different nodes. Then we define a set of graph patterns. So by applying graph patterns in text graph, we'll generate many semantic links. You'll see that actually the semantic links are kind of an initial version of infobox. But first, the link name in semantic links is directly from the sentence, so it's not standard ones, and it's not ready to directly use it for structural queries. And also there are many redundant information there. So we annotate the text and then use existing infobox to generate infobox patterns. The function of infobox pattern is tell us how to map the link to correct attribute names. So we apply these infobox patterns to semantic links and remove all redundant information. Then we generate our final infobox triples. To evaluate the performance of our system, we apply IBMiner onto the text of entire English Wikipedia corpus. So we use about 4.1 million articles, and for each article, we use at most 200 sentences. We employ UCLA Hoffman 2 cluster to perform this experiment, which took about 2 weeks, and it generates about 251 million of semantic links. Of course, there are many redundant information there, so we filter these semantic links, and finally we have about 7 million triples. So we sample a part of these triples. We sample about actually 50,000 triples and manually grade them. So the accuracy we got is about 90%. And after we get the knowledge from different sources, like knowledge integration and text, we already have a good quality knowledge base. But the problem is that in many phases, the human effort is still required to validate and improve the results based on the correctness and significance, because in many situations we'll generate, say, two similar infobox. So only human being can judge which one is more important for users. For this case, we developed two interfaces. The first one is called the Infobox Knowledge Base Browser. this browser can allow users to browse info box, category information, and provenance. And also we developed info box editor to generate info box and suggest category information for input article. So in other words, user can just write a few sentences, then we will generate the info box and suggest category information in real time. It's very convenient for Wikipedia editors. And so we move to the usability problem when we face such a big knowledge base. For users who are unfamiliar with the entire knowledge base schema and the SPARQL, the search could be a very serious problem because they don't know how to write the query conditions. The solution proposed by Professor Carlo is called SWIMS. Basically, it extends query by example approach so that users can explore the existing info box as input query from an example page. For example, we would like to find all the universities with more than 2,000 faculty members and established before 1900. So for SWIMS system, user can just first find an example page, like maybe you can first try UCLA. Then from the info box of UCLA, we find the attributes which represent our query conditions. The first one is established, which is for this condition established before 1900, and also the academic staff, which represents the condition number of faculty members. So to represent this query, user can directly click on the values in these attributes and fill in their query conditions as these ones. Later, Dr. Massimo will give a short demo of this web system. So next part of our framework is the support for temporal queries over historical knowledge base. Because as the world evolves, the information in our knowledge base is changing all the time. Like if we look into the Wikipedia of Santiago, we find that, for example, for the attribute mayor, its value changed every year. So sometimes user may would like to query this evolution history to retrieve the snapshot of historical knowledge base, and sometimes even perform analysis over the historical knowledge base. So we propose an extension of SPARQL language called SPARQL-T. This extension can help express powerful queries over temporally enhanced RDF triple, like temporal selection, temporal projection, temporal join, and temporal aggregates. Similar to SPARQL, this query language is maybe a little complex for normal users. So we extend SWIMS system to support the query by example search. The right image is just an example of our interface. User can just click on the attributes to see the historical information, and also if user put on some time constraints and temporal variables there, then our system will automatically generate equivalent temporal queries. At last, this historical knowledge base could be very large. For example, we just generate a subset of historical knowledge base of Wikipedia. It has about 40 million triples. So to make the query evaluation very efficient, we develop in-memory query engines with full temporal index support for SPARQL queries so that user can get their result very quickly. And next, Dr. Massimo will introduce our parts of SWIMS system and natural query ANSI.
Hello everybody. I'm Mazzeo, and I'm going to show you a demo of swipe system. Imagine that a user wants to find the musicians who were born in Los Angeles. By using Wikipedia, he could use the text search provided by Wikipedia, and he can write in the keyword search box musicians born in Los Angeles, then submit the query, and Wikipedia will show some relevant results such Kelly Peters, and many not relevant results such as Los Angeles, South Los Angeles, Los Feliz, and so on. This happens because this is a keyword search and not a semantic or structured search. Instead, with the by example query paradigm of swipe, the users who want to find all the musicians born in Los Angeles can just start from an example page of, for instance, a very famous musician such as John Lennon. And then in the info box, you can set the birthplace with Los Angeles. And since he's interested in just in the musicians and not all the people born in Los Angeles, he set the type of the results, which is musical artist. Then by pressing the swipe button, swipe system shows actually all the musicians who were born in Los Angeles. Now imagine that the user wants to find the musicians born in Los Angeles who won a Grammy award. If we look at the info box, there is no way to set the condition about the Grammy award, but swipes can combine the structured query with text search. So if we type Grammy in the dedicated box, swipe will find for the word Grammy in the abstract. You can see this constraint, and we still have the conditions about the birthplace and the type of the results. So in this way the user can obtain the results in which he is actually interested. The combination of structured constraints in the info box and keywords in the dedicated keyword box enables swipe to provide very precise results. The only effort that a user must make with swipe is finding an example page and setting the constraints. However, we are currently working at an extension of swipes which makes the system even easier to be used. Specifically, we are trying to enable the user to initialize swipe searches using the natural language questions. For instance, if the user is interested in finding which films directed by Gary Marshall was Julia Roberts starring, he can just type the question in a dedicated search box, and then swipe will be able to show an example page, for instance the page about the Pretty Woman movie, with the two conditions set in the info box, like this. Then the user, if needed, can refine the conditions and submit the query as usual, thus obtaining the results. In order to achieve this goal, we are following an approach which consists of 3 steps. The first step is understanding the type of questions. Specifically, there are many ways to ask questions, and we have defined a set of patterns where each pattern represents a class of questions which can be processed in a similar way. We have defined 35 patterns which cover all the 450 questions of 2 very famous benchmarks, which are QALD 3 and 4. The second step is the interpretation of the question. Each pattern can be interpreted in several ways, and in the second step, all the possible interpretations are provided, and each interpretation is represented by a semi-formal query, as we will see in the following. Then, in the third step, the interpretations are mapped over the ontology, and the correct interpretation is found. Let's see by means of an example how the system will work. For instance, consider this question: in which films directed by Gary Marshall was Julia Roberts starring? This is a specific case of a general class of questions with the same syntactical structure, where we have a preposition in, a WH pronoun which, a noun phrase 1, films directed by Gary Marshall in our example, a form of the verb to be or to do, was in this case, a noun phrase 2, Julia Roberts, and a verb starring. There is one high-level interpretation for this pattern, that is, the entities described by noun phrase 1, namely films directed by Gary Marshall, are bound to entities described by noun phrase 2, Julia Roberts, by means of an attribute described by the verb and the preposition, that is starring in. In order to obtain the detailed interpretation, we have to generate the interpretation for the noun phrase, for the noun phrases, which can have several interpretations. The correct interpretation for this question is this one. E1 is an entity, is a film, E1 is directed by Gary Marshall, and Julia Roberts starring in E1. But another possible interpretation for the sentences with the same syntactical structure is this one. E1 is a film, E1 is directed by Gary Marshall, E2 is starring in E1, and E2 is a Julia Roberts. In this case, clearly this interpretation makes no sense, because Julia Roberts is a specific entity, not a category. But this question, the first question, has the same syntactical structure as the following question: in which films directed by Gary Marshall was a singer starring? That is, Julia Roberts here should be replaced by singer, so the correct interpretation would be this one and not this one. The correct interpretation among all the possible interpretations is found in the third step. So far we have worked at the first 2 steps, and we are going to start to tackle the problem of the third step. In conclusion, SWIMS is an integrated set of systems and tools which enables to extract structured information from natural language text, which enables to integrate information from different knowledge bases, and provides a user-friendly and very precise query interface, user interface. Our current work is focused on extending the support for query historical knowledge bases, for providing a user-friendly natural language interface, and we started investigating the problem of applying the IBMiner systems to scientific and medical documents. Thanks for your attention.
Thank you, guys. That's a very cool tool.
Yeah.
Are there any questions from the audience?
Hi, this is Sarah Scruggs. Thank you very much for that talk. That was very stimulating. I just had a quick question. I've been working on the GeneWiki project for BD2K. And as much as I love the Hollywood examples, I was wondering if you could use sort of if you could show us an example of how you might apply this swipe technology to, like, say, a gene page. One of the genes that we've been working on, for example, MYH7. Could you show us an example like that? Because the info box is structured differently, but I wasn't sure if you would be able to.
You mean like applying swipe to a gene page?
Yeah, to one of the GeneWiki pages.
I think we can have a try. I'm not 100% sure if we can find all these results. But Max, could you try maybe a gene page?
Well, actually, Swipe is an interface which makes easy to query the DBpedia knowledge base. So, if the attributes are present in the info boxes, then they will be also in the DBpedia knowledge base, and it will be possible to query them. If these attributes are not in the info box, there is no way to, at least with our approach, to create meaningful queries, because the Swipe is just an interface which relieves the user from writing SPARQL queries. But of course, if user is looking for different information, it cannot find this through Swipe or neither through DBpedia.
Okay. Is this something where, I guess, sort of a big picture question with regards to BD2K, the project, could you sort of give us just sort of a big picture of how this wonderful and very sophisticated technology will work into sort of the BD2K overall?
I think I may answer a little bit. So first is that for BD2K, there are many existing knowledge bases in the medical domain and the drug domain. And they are like separate projects. And first, we would like to construct a professional knowledge base for drugs. And we are working on it. We are collecting the knowledge from the Wikipedia drug category, from the drug banks, and also from other knowledge bases. And with this knowledge base, as Max said, we can build another like swipe system for the medical domain, so that users can just click on example page and search the information, maybe the drugs, maybe the doctors, maybe hospitals, search this kind of information using our integrated drug knowledge base. Another part is that we are cooperating with the UCLA Medical School to build some information management systems for hospitals and the doctors. So that's our ongoing work.
That's very nice, very cool. Thank you.
I have a question about DBpedia. So I noticed that in DBpedia I search for things like hemoglobin, and then they have Wikipedia articles, but they don't show up in DBpedia. I thought the DBpedia was automatically constructed from the contents of Wikipedia info boxes. And like the protein in the Gene Wiki project, they have pretty in-depth info boxes.
The problem of DBpedia is that first we have a semi-automatic approach to construct DBpedia. So basically, we try to pass the HTML web page and grab the info box part from Wikipedia. But this system is not perfect. Actually, we find that for many domains like drugs, like genes, the system cannot recognize many values in the web page. For example, the formulas, especially the chemical formulas, the complex names. Sometimes we recognize these things as people name, as a place name. So basically, there are many incorrect information in Wikipedia. That's what we are working on, trying to improve it using the info box from the text part. And yeah, basically for domains, we collect some stats, and we find that only 45% of info box are correct, and the rest ones are totally wrong. They have some wrong attribute names or wrong values. So we need some effort to make it available or ready to use for structural query engine.
Okay, thank you.
Are there any other questions for Shigao and Giuseppe? Okay, thank you for that great presentation. We'll move on to our second presentation. Our second presentation will be presented by Chelsea Ju. Chelsea received her bachelor's degree in biological sciences at the University of Alberta, Canada, and a master's degree in computer science at UCLA. Currently, she's a second-year PhD student in the Department of Computer Science at UCLA, supervised by Professor Wei Wang. And today she will be presenting about the metabolomics data analysis in heart failure patients. Using metabolomic profiles, the study aims to identify and characterize the factors which correlate and or contribute to different clinical performances of heart failure patients after implantation of MCS. Without further ado, allow me to introduce Chelsea.
Thank you, Vincent. Can everyone hear me?
Yes, we can hear you very well.
Okay, awesome. So thank you everyone for attending as well. So today I'm going to give a talk basically focusing on a project part of the BD2K, focusing on the tool development for analyzing the metabolomic data for heart failure patients. So some of you may have already heard about this in my in the NIH meeting. So for those of you who haven't, I'll give a brief introduction of what I've been working on. So a little bit of the background information. There are more than 6.6 million heart failure patients in the United States, and 80% of them are hospitalized, and 50% of them actually died within 5 years of diagnosis. And mechanical circulatory support is one of the treatments for heart failure patients. However, many patients develop multiple organ dysfunction syndrome after the implantation, and this is actually one of the major causes of death for this kind of treatment. The advanced heart failure is often clinically treated as a homogeneous disease with similar treatment options, but recent studies have suggested that heart failure is a heterogeneous syndrome that may require divergent therapies. One of the issues is that accurate phenotyping and classification of advanced heart failure is still preliminary due to the lack of validated and quantifiable methods. And the reason we use metabolomic to study clinical heart failure is that it's relevant because we can use the metabolomic profile as a guide to, to find out, basically to find out the biomarker with respect to diagnosis and therapies. And we can also use the profile for patient stratification and clinical classification. And they also provide a mechanistic insight for the complex pathophysiology in cardio remodeling and failure. And there are many other more advantages using the metabolomic profiles. And therefore, the aim of our study is to use these metabolomic profiles to identify and characterize the factor which correlate and contribute to different clinical performance of heart failure patients after the implantation of MCS. So in our study, in our analysis, the data actually came from a time series of blood samples collected from 12 healthy participants and 26 stage 4 heart failure patients according to the New York Heart Association functional classification. So in another word, these patients, they are in their worst stage of heart failure. And we screened for 611 metabolites. So 611 metabolites are quantified for each samples. And the pie chart below shows the demographic information for our participants. So there are 77% of the patients are male and 23% of them are female. And among our healthy participants, 76% of them are male and 33% of them are female. And the race for our participants includes Caucasians, Asian, as you can see on the right side of the figures. So they include Caucasian, Asian, African American, and Hispanic. And since we're using a time series sample for our study, individuals are sampled throughout various different time points before the surgery and also up to 120 days after the surgery. And the diagram here shows the time interval between the time point collection. So we use T1 to denote the time point before the surgery, and T2 basically is up to 5 days after the surgery, and T3 is up to 11 days after the surgery. And most of the healthy participants are sampled up to T5, which is 24 days, and the patients are sampled as long as they're hospitalized. So some of the patients are released earlier because they got better, and some of the patients didn't make it until the end of the study. So for the purpose of the methodology development in our process, we only use a subset of the data in our analysis. And this subset of data contains 12 healthy participants, which is all of the healthy participants we collect, and 15 advanced heart failure patients. And since all of the healthy participants are sampled up to T5, so we focus on our analysis on the first 5 time points. And the analysis we carried includes differential expression analysis and the pairwise correlation analysis and principal component analysis. And then I'll describe each method, each analysis below. So the first question that we're trying to see is whether we see a distinguished pattern or whether we see the differences using the metabolomic profile between the patients and the healthy participant. So the goal for this differential expression analysis is to identify a set of metabolites that are significantly differentially expressed between the healthy participant and the heart failure patient at a given time point. The approach we use is using a student t-test. So we apply the student t-test on each metabolite to evaluate the significance of the changes between healthy participant and the patients. And since we apply this statistical test on every single metabolite, we need to correct for the multiple testing issue. And we use Benjaminic and Hopper procedure to control the false discovery rate. And the final list of significantly differential expressed metabolites are chosen based on the two criteria. One is the adjusted p-value has to be smaller than 0.05. And the other cutoff we use is the absolute fold change. So the fold change has to be 1.5, has to be more than 1.5. So we apply this analysis on our T1 data. That basically is the time point before the surgery. And the results is shown in this volcano plot on the right. There are 196 metabolites identified as significantly differentially expressed. And the volcano on the x-axis of the volcano plot shows the fold change between patients and healthy participants in the log2 scales. And the y-axis shows the p-value in a negative log10 scale. The vertical line here shows the cutoff of the fold change. So we only keep those metabolites that are bigger than 1.5 of the fold change in log2 scale. And the horizontal lines here shows the cutoff of the p-value. And there are 80 upregulated metabolites in the patient, which is highlighted in green in this figure. And there are 116 downregulated metabolites in patient, which is highlighted in red in this figure. So we take a closer look at this differentially expressed metabolites. We take a look at the expression pattern between basically we take a look at the expression pattern of this metabolite that we identified. And we use a heat map to illustrate this. And on each row represents the metabolites here, and each column represents the participant, the individuals we have. And the healthy participants are grouped together as highlighted in blue in this figure. And the patients are grouped together highlighted in red in these figures. And we can tell that using this set of metabolites we identified, we can see a very distinct pattern between the patients and the healthy participants. And the next things we try to do is we try to look into what classes of these metabolites belong to. So we plot this out in this figure. On the x-axis shows the different classes of the metabolites, and the y-axis shows the number of metabolites in each different classes. And this set of metabolites are identified across 20 different classes over here. And we notice that there's a large number of phosphatidylcholine downregulated in the patients, as highlighted in the red arrow in this figure. And a high portion of acylcarnitines are upregulated in the patient, as highlighted in the green arrows over here. So phosphatidylcholine is by far the most abundant dietary sources of choline in most humans. The actual mechanism is still unclear, but choline is linked to the synthesis of homocysteine, which is a known cardiovascular disease risk factor. Acetylcholine and methionine deficiency in rodent model cause lipid accumulation in liver, heart, and arterial tissues. And there's a study suggests that manipulating the metabolism of dietary phosphatidylcholine may be a novel therapeutic approach for heart disease. And another study also suggests that one of the phosphatidylcholine species, DLPC, is a promising therapeutic agent to improve diabetes. And acylcarnitine is a class of essential compound for fatty acid metabolism. And again, the actual function is still unclear, but it is known to be involved in fatty acid oxidation pathways. So in next of our analysis, as an explorative approach, we apply a pairwise correlation analysis with the goal that we're trying to explore the expression pattern of all metabolites across different time points in patients and healthy participants. So the approach we used, the first step is trying to retrieve the expression profile for each metabolite. So here, the expression profile is defined by the quantification across different time points for different individuals. So as illustrated in this table, each column indicating the expression level of a metabolite at a given patient at a given time point. And the expression profile of a metabolite can be identified as the whole row. So each row represents the expression profile for different metabolites. And we calculate the pairwise which basically calculates the Pearson correlation of each pair of metabolites based on the expression profile. And the pairwise correlation is plotted is right now in a correlation table. As we can see that the diagonal shows the correlation with itself, so it will be 1 on the diagonal, and the off diagonal is symmetry. And the next things we do is we apply a hierarchical clustering on the correlation coefficients so that the metabolites with similar correlation coefficient are displayed right next to each other. And we displayed the result in a heat map using two different spectrum of colors. So the dark blue shows a strong positive correlation between the two metabolites, and the dark red color shows a strong negative correlation between the two metabolites. And we applied this approach on our data, which contains basically applying on all the metabolites and using the expression level across different patients and different time points, different individuals and different time points. And we plotted out in this heat map. So on the x-axis and the y-axis shows the metabolites to itself, and the diagonal, basically we see a very dark blue color on the diagonal because they indicated the correlation with itself, so which should be 1. And we also observed 5 subgroups from this heat map, which is indicated by the dark blue patches along the diagonal line. So we take a closer look at those 5 subgroups, and we notice that one of the subgroups is dominated by the phosphatidylcholine. So as indicated here, like one of the big blue patch along the diagonal line is dominated by the phosphatidylcholine. So in order to take a closer look, we plot out the expression pattern, expression value across the time in using all the patients. So from this plot, the x-axis indicated the days from the surgery, so 0 date indicating the surgery date, and the negative indicating the day before the surgery. And all the positive basically means that it's the day after the surgery. And the y-axis indicated the expression change. So the changes is related to the time. It's related to the time point before the surgery. And we plot out basically all the patients, the expression for all the patients, and the different patients are indicated by different colors over here. And another interesting group to look at is on a small, like basically on the middle of our heat map, which is also another blue patches along the diagonal, that this group of the metabolites are dominated by the acylcarnitine. And again, we plot out the expression changes across different time points using all the different patients. So some of the things that are still working in progress related to this pairwise correlation analysis is that we would like to further divide those 5 subclusters into a smaller group, because as we can see from the heat map, that some of the subcluster may show some interesting pattern because they have a stronger correlation with each other. And it's kind of hard to say why. It's kind of hard to tell like how many subclasses that we should cut it into. So another good way to do it would be performing an enrichment analysis to further examine those functional impact of this cluster. So as we are working along with developing with different methods for the data analysis, one of the key questions that we're trying to answer is to identify, to discover a set of influential metabolites that can distinguish the patient and the healthy participants at different time points. So we carry out this principal component analysis because PCA is known for PCA is a known data reduction technique. So we're hoping that we can reduce the set of metabolites into a smaller set that are mostly influenced they're most distinguishable between the patients and the healthy participant. So the first step of the principal component analysis is to carry out a data normalization, since the absolute quantification values vary a lot for different metabolites. And the quantification, the normalization is carried out by minus the mean of the quantification of that metabolite and divided by the standard deviation. And after the data normalization, we directly apply the PCA on all the normalized quantification and project the individual to the new coordinates based on the first two components, as we know that the first two components shows the most amount of variation in the data. And the patients are further divided into 3 groups based on their clinical performance, which is judged by a UCLA clinician. So they're divided into poor, median, or good. And each time point is plotted separately. So here is the result shows using a time point 1, which is the before surgery. And we can see that using the PCA approach, we are able to separate out the healthy participant from our patients. However, the distinction among the patient performance remain ambiguous, as we can see that patients with different performance, they're still clustered together in this plot. And the same thing we observed at different time points. So we applied this to time point 2 up to 5 days, time point 3, time point 4, and time point 5. And as we can see that PCA is able to separate out the patients from the healthy participant, but the distinction among the patient is still ambiguous. So some of the limitation we observe using the principal component analysis is that it's unable to separate the patient with different performance. And one of the potential solutions is to look beyond the first 2 components, because maybe the true variation is actually lay in the PC3 and PC4. And the second limitation is that we're unable to pinpoint a specific metabolites. And some of the potential solution, as we're still working on it, is to explore other techniques to combine the techniques with PCA or feature extraction. So one of the techniques that we're exploring is that we should apply, perhaps we should apply differential expression analysis first and then see how it behaves on the principal component analysis. So some of the future works that we're working on it right now is since all the data right now is on human, and we'd like to conduct the parallel analysis on the model organism. For example, the data we have so far is 6 strands of mice who receive isoproterenone treatment to induce the cardiac maladaptive remodeling. So basically, this group of mouse are trying to make the heart remodeling process. And as I mentioned earlier, that we'd like to focus more on the differential expression analysis, maybe to compare the healthy participant versus the patient, and also compare the time points. So for example, the time point versus the time before the surgery. And we also like to incorporate other types of data to augment the finding in metabolomic analysis. For example, perhaps we can include the genotype information to correct for population structure in our study. And with that, I would like to thank my supervisor, Professor Wei Wang, and also Sapit, who is a PhD student in our lab. And also this project is a very close collaboration with Dr. Ping's lab. So I'd like to thank Professor Pei Ping and Dr. David Lim for giving me a lot of information, providing the information for the patients, and Howard, who's a PhD student who helped me a lot with the data analysis as well, and Dr. Ding Wang and Dr. Travis Cho and Jennifer Paulson for providing all the metabolites insight for the function. And thank you very much for your attention.
Thank you, Chelsea. That was a great presentation. Are there any questions?
Hi, this is Dr. Isigi. Can you hear me?
Yes, can you speak up a little bit?
I'll try to. I have, first of all, a very nice presentation, and for sure you are demonstrating the potential of the approach that you are using. Couple of questions/comments. I would like maybe to bring up the issue in the t-test that you use, that you put 0.05 the cutoff, whether that is not hard enough, and so that you're using a 600 metabolites, all right? If I recall properly the number or something in that range.
Yes.
And so you're putting as the number of fast discovery that you have 30 to start with, just based on probability that you are putting as a cutoff that are going to be fast discovery. So that to me sounds a bit high. So I'm wondering if maybe you explore doing the same type of work but using higher cutoff.
So I would, you're saying with the false positive discovery, or?
Well, in your first T-student test, you put a cutoff of 0.05, right?
Yes.
Which has about 5 out of 100 by chance are going to be identified as they're false positive, so they're not. The probability is that they're not real differential. That there are no real differences, but it's just by chance because you have such a high number of metabolites they're looking at.
Yes.
So
yes.
Just by chance, since you are looking at 600 metabolites, you have about 30 analytes or metabolites that are going to be false positive or identified just by chance, at least that are not going to be real differences. So to me, that my first reaction would be that's maybe a bit high. It is true that you go farther, so I don't know how you fit into that. You go farther in doing your volcano analysis and you identify only the ones that are 1.5-fold differentiated. So I don't know how it looks like. So if you would use 0.01, maybe you have some more constraining set of metabolites to start with. I don't know, just
That's a very good point. So one thing is that we do apply the multiple testing correction to correct for the false positive rate because of the basically because we have a high number of metabolites here. So the cutoff is actually on the adjusted p-value. So after the multiple testing correction, and we use 0.05 is just to be a little bit more conservative because we want to see what kind of metabolites we identify at first. And I totally agree with you that 0.01 is a much more stringent cutoff so that we can narrow it down to a smaller list and then to see so that we can have a higher confidence about that too. I think we looked into it because this is actually analysis carried out for me and Howard, and I think we had the data there, but we probably haven't spent that much time looking into it yet.
No, it's something that just maybe to look into whether and So I'm not certain. That is maybe more difficult to assess because you're also using later cutoff, which is you are looking at the one that are the how did you define it? I think the most relevant differences. I think you use only the one that are at least 1.5 folds, right?
Yes. Yes. Yes.
So probably that remove also some of the false positive, and I'm not sure where it's the right balance there, but personally, I would rather to have only 10 metabolites that are really very strongly that are quite certain to make a difference. Maybe even using as you did later the analysis in looking them couple like just 2 other times or things like that, than having 190. But I don't know, something to think about. The other one, something that I'm not certain is, and probably you do have them. I'm by far not an expert in cardiology. So what could be the practical utility? So you mentioned that there are 3 categories of poor performer, good performers, and low performers, right?
Oh, yes, on the PCA, yes.
Trying to guess what it is there, the actual utility that you will have at the end, but I'm not certain. So would it be useful indeed? Is that what you're looking for, a marker that will tell you for the difference between poor performer and good performer, because that once that you have after surgery, once that is identified, that would be practically useful and potentially do a different treatment? Is that the aim?
That's actually one of the aim we have in mind, but we haven't really narrowed it down to the analysis to identify that part yet, and that's why we're just like right now we're just looking for more of the explorative mode to see what we see so far. But yes, that's actually one of the aim, hoping because as I mentioned earlier, that a lot of the patient develop multi-organ dysfunction syndromes, so perhaps judging based on their performance throughout the surgery, we may be able to tell that whether this patient may be able to make it or not, or is it worth the time to continue with the surgery or not.
Right. Yeah, no, that's I think that's a possibility. But then you would have to keep in mind that if that is what you're looking after, so the sample that you need to look where you need the marker is the one prior to surgery. So what is important is that in your analysis you keep in mind exactly what it is, the endpoint and the use. That is something that's been criticized in the last few years on many biomarker studies have been published also. That indeed not always taken in consideration from the beginning of the analysis what it is, the actual endpoint and use, because that I think will make your data and analysis much stronger. I know that you are still very exploratory study, so it looks great, but by all means, it's a great job. Just making a suggestion.
Thank you very much for the suggestion.
Hello?
Yes.
Yes,
yeah, I also have a question. I'm Rafael Altara from University Medical Center of Mississippi. I'm wondering whether I guess you have collected also BNP values of these patients, and whether you have a time course of the BNP, which I assume will get low after the operation, and whether you have higher and lower responders, and whether you can correlate with your metabolites.
Yes, we do have something related to BNP. They call it the SOFA score, so they actually judge based on a bunch of different things. I don't really know the detail. I'm not sure if David is online to help me answering this question.
Hi, this is David. Well, we do have BNP values, and one of the things that we've been discussing is that we can correlate everything to the BNP values, since those are actually standard clinical biomarkers to define heart failure.
Right.
In addition to that, what Chelsea also mentioned, we do have SOFA scores that indicate actually the overall clinical assessment for every time point that we have. So we're doing actually, we're looking actually at both, basically. We're thinking about both.
I see. So, but do you know whether you have like high or lower responders of BMPs?
So for sure that most of the patients actually, after the assist device is implanted, show that the BMP value go down because of the unloading of the heart. But that is just a pressure unloading, and of course the BMP will go down. But that doesn't mean that the SOFA score, improves, because the SOFA score actually still indicates the overall clinical, picture of the patient. You see, so in that way, it is still a little bit, we're discussing that. But like I said, the BMP values all go down. That's normal. That's a physiological reaction. But the SOFA score still is actually the real overall clinical assessment.
Okay.
Thank you. Does that answer your question?
Yeah. Thank you very much.
I would like to, since I'm already speaking anyway, I would also like to make a little comment on the previous question about the biomarker development that we are actually also thinking about. I think the purpose of the study is actually, it has several, we have several aims. And one of the aims is, of course, the biomarker discovery. And we are already actually measuring all the time points after the implantation of the assist device, and then measuring that and comparing that to the time point before the surgical implantation, meaning that when the patient is having severe heart failure, so that's time point 0, and and then we have several other time points after the surgical implantation as a therapy, and then we're comparing all these time points to the time point 0. So in that way, that that would be, I think, in our opinion, a good venue to do biomarker discovery. So picturing the whole patient from the beginning, before the implantation, and then follow up after the implantation up to 10 time points. So we do have that, and we do that in several ways for biomarker discovery. And the second aim is, of course, with all these metabolites that we are actually analyzing, that we also look for mechanistic insights.
Thank you so much, David, for jumping in.
It's no problem. We're working together, Chelsea.
Yeah, and thank you so much for all the questions, too. And I don't know if we have time, but I'm happy to take more questions as well.
Okay, yeah, any last questions for Chelsea? Okay, thank you, Chelsea, for a great presentation and great discussion. So this concludes our conference for today. Next week we'll have Train Online and also the European Genome Archive presenting next week. Thank you all for attending.
And we will we'll be starting a half hour earlier, correct? So
yeah, I'll send out an email next on the
okay, yeah, the time will be slightly different. Also, there's the videos. There are people that have trouble viewing the videos on the Google Drive. So there's a YouTube channel that I'll post here in the chat, and this has all of the conferences we've had so far. They've all been uploaded there.
So we'll also post that link on the Trello board, so you all have access to the videos. Let us know if you have any questions, either now or through email. Yeah, thank you. Thank you for attending this conference.